This is Unit 4.8, Earth's Geography and Climate. You'll notice if you look at a broad description of Earth's climates that we describe them as tropical, subtropical, temperate. This has to do with temperatures, of course, where tropical climates tend to be near the equator, subtropicals north and south of that, and so on. And we'll see that climate patterns are really the result of multiple factors that we've discussed in the last few videos. So climate patterns are determined by the angles of the sun's rays, right? How much sunlight, how much sun energy, how much light energy the Earth is receiving from the sun, right? Where the sunlight strikes most directly, there's more energy. Global air circulation affects climate. Um, so the air circulation, the Hadley and the Ferrel cells, but also the Coriolis effect. The air is distributed widely over the Earth, and it carries water with it. As the water cools or heats, that can release water or absorb water as well. And finally, ocean currents also determine climate patterns as they carry warm or cold air or warm or cold water that can affect surface air, which affects climates in certain parts of the world. We'll talk about that relative to Europe, for example. Main issue is that heat and precipitation are distributed unevenly over the Earth. And so a lot of movement of air and water is water or air that is very hot trying to get to places that are cooler because of the laws of thermodynamics. There is interaction between the atmosphere and the ocean that affects climate. So, of course, there are deep currents that are created by density differences in hot and cold water and higher and lower salinity, right? So, hot water is less dense and fresh water is less dense. So, hot fresh water tends to rise, and then cold water or highly saline water is denser. So, cold salty water tends to sink. And that creates convection currents in the ocean. Now, these are the deep currents, right? These are not the surface gyres, which tend to be dominated by surface winds. But the deep currents are dominated by density differences in the water. And so these interactions can vary over different time scales, right? There can be seasonal or annual ocean currents. But then there can be interactions that are over numbers of years. Like El Nino is a longer time scale ocean interaction. And then finally, there are interactions that can happen over decades or even longer, hundreds or even thousands of years. Some deep and shallow ocean currents have this interaction on the Earth, where you can see the warm, fresh water that's closer to the surface. And what happens is the water in the Pacific Ocean tends to flow, when it's warm, through areas of Indonesia into the Indian Ocean, south around Africa, north through the Atlantic. But then when it gets up into the North Atlantic, north of England and so forth, it starts to cool down. And as it cools, it takes on more salt and it tends to sink. And then as it's deep in the ocean, it circulates back down through the Atlantic, through the Indian Ocean, through the Arctic into the Pacific. And so the deeper water tends to be colder, the shallow water tends to be warmer, and we have this fairly large, global ocean current. There's a good video on this that describes how this works and also some of the effects. One of the main ones being that even though Europe is a fairly high latitude, compared to the United States, right? France is about the same latitude as Washington State, right? And you might think of Washington State as having a fairly chilly climate. But in Europe, it's fairly moderate because of the Gulf Stream carrying warm water and warm air. Topographic features can also affect climate. So mountain ranges are really good at this because they tend to block water. So let's say there are prevailing winds coming from the ocean. Those winds tend to have a lot of water. And as the winds push up against the mountains, the water doesn't get over the mountains, partly because of the rise in altitude, right? As that air goes higher, it cools and the water vapor condenses. So on the windward side of mountain ranges, you tend to get more rainfall. And then on the leeward side, where is opposite the wind, there's less rainfall, and so it tends to be more deserts. So you can see this in places like California, where the winds are blowing the water, are carrying water onshore, but then the mountains block those winds from carrying the water further, and you get deserts in places like um, Arizona. So we can see this in more of a cross section. Here's lots of different graphics that you can see this effect. And this is what's called a rain shadow, where the water is dropped on the windward side of the mountains, and then there's no water as the wind goes over the mountains. And so there's no rain on that side. So that is the rain shadow. Rain falls on the windward side, rain shadow on the leeward side. All right, well, that is Unit 4.8. Please let me know what questions you have.